Good morning, everyone. My name is Patrick Baker. I'm a professor of silviculture and forest ecology here at the University of Melbourne. I'm also the director of the AFWI Center for Climate Smart Forestry. I'd like to thank everyone for joining us today for what I'm sure is going to be a fascinating seminar. I'd like to begin by acknowledging the traditional owners of the lands on which we work, learn, and live, the Wurundjeri, Woiwurrung, and the Bunurong peoples. We also acknowledge their enduring cultural practices of caring for country, and we pay our respects to their elders past, present, and emerging. Today's seminar is hosted by the AFWI Center for Climate Smart Forestry. AFWI, for those of you who don't know, stands for the Australian Forest and Wood Innovations, which is a Commonwealth-funded program managed through the Department of Agriculture, Fisheries and Forestry, DAF, to build research and research capacity to support Australia's forest and wood products industry. Australia's forest and wood products industry is in transition. Decades of social, cultural, and environmental change have profoundly altered the landscapes in which the forest industry works. Social license is at an all-time low. Imports of wood and wood products are at an all-time high. Regional communities that depend on forestry are declining, and the forests themselves are being profoundly impacted by intense fires and droughts at spatial scales and frequencies that have rarely been seen before. The mission of our center, the Center for Climate Smart Forestry, is to provide national research leadership to support Australia's forest and wood products industry as it adapts to increasingly unpredictable and extreme climatic conditions and the growing recognition of forest's role in mitigating climate change. Climate Smart Forestry is a forest and land management framework to enhance the role of forests in climate change mitigation, to support adaptation to changing conditions, and sustainably increase forest productivity and resilience. It has three core components. The first is increasing carbon storage in forests. The second is enhancing forest resilience and therefore the persistence of that carbon in the forests through management. And the third part is using sustainable wood resources as substitutes for non-renewable carbon-intensive resources such as petroleum products, concrete, and steel wherever possible. So this is a relatively broad church in terms of what we are thinking about in our research center. Carbon, however, is a central theme in our center. So today I have the real pleasure of introducing to you two of our colleagues, Rob Waterworth and Geoff Roberts, both co-founders of FluentPro. For decades, Rob and Geoff have been at the forefront of thinking about carbon in Australian forests and forested landscapes. Rob is Deputy Director of our AFWI Center for Climate Smart Forestry and co-developer of FullCAM. Geoff has been working on carbon and land sector reporting in Australia for nearly 2 decades. Both are foresters by training and modelers by choice. They've been instrumental in the development and application of models to support carbon and carbon accounting in Australia. And today they're going to talk about all things FullCAM. And so with that, I'll hand over to Rob, who I think will kick off. And I just would like to thank you all again for joining us. And I think this is going to be a fascinating day of learning about FullCAM. Thanks very much.
Great. Thanks very much, Patrick, and thanks to everyone who joined. Look, I was just going to start off with a couple of brief comments before we jump in here, which is obviously, as Patrick's just said, AFWI is looking a lot at carbon and the impacts of forests on the carbon cycle and where we can make improvements and obviously large impacts on the issue of climate change. In Australia, one of the core issues around that, of course, is FullCAM. FullCAM is a core component of everything that happens when it comes to carbon accounting in Australia. And it's been around for a very long time. And one of the key things we're really interested in making sure is that everyone has a really deep understanding of what it is and what it isn't. As we started to look more at some research programs and some proposals that were coming through, and from Geoff and my decades of getting phone calls about it, we were starting to realize that there was actually a lot of interest in FullCAM, but also a fair degree of misunderstanding. And so we thought it was very important to try to get everyone to a core base of understanding around the system. And as part of that, we realized there was a real need in the broader community as well. So we thought that would be a really useful thing to open up this morning so that we could share all this experience. I want to be really clear that we're not representing the department here. That also we're mainly going to be focusing on the tree components of FullCAM. FullCAM does a lot of agriculture and other components, but we're really going to focus on the tree components. Otherwise, we could be here for days. And finally, you will find a lot of the slides quite text heavy. we have done that on purpose, primarily because we're going to make the slides available so the people, and we just didn't want to be talking to a couple of dot points. So I won't be reading off the slides specifically, but really trying to get into that. And the final point with the slides is you will find some probably misalignment in some ways on tense. And that's primarily because a lot of these slides I've just redone from things that were presented between 2006 and 2010. So, but most of it is still very current. So with that, let's get on to it. So as I said at the start, the first thing that Geoff and I really wanted to get to is, confusion around things always causes misconceptions. So Geoff and I quickly came up with a list of, well, what 6 things that we hear a lot about FullCAM that aren't necessarily the case. And here, I'm not going to read these out, but these are just 6 ones we hear a lot. And today we're actually going to run through the system. And by the end, you should see that these really aren't the case. As a little bit of background, I thought I'd sort of talk a little bit about my pre-FullCAM NCAS days, because that gives probably a bit of context. And of course, as with anything with forestry, it's important to have a photo of yourself with a child planting a tree. This was part of a program called Bush for Greenhouse, which was when I started working around FullCAM very heavily in 2000. So I originally did forestry at the University of Melbourne. So like all University of Melbourne forestry graduates, I went and worked in the statewide forest resource inventory. Gave me a really deep interest in the issues of modelling and measurement. And some of my early research was on, how well does DBH relate to basal area, for example, when you get into large eucalypt trees? Answer is pretty poorly. And what's the implications of that? I started playing a lot with CO2 fix, which was very useful, as you'll see later on. It was an early model out of Europe. Also, fortunately, did a lot of work on the biology of forest growth experiment through these times. And so was able to gain a fairly deep understanding of a variety of models, a lot of which were developed off that, be it a 3PG, a KenW, Kabbalah, et cetera, all of those I had to play with on those. So, and then obviously brought that into FullCAM. So I really moved from being a measurer to a modeler. And as I say, with all of these things, you want to be careful of the reformed in this case. So take that as hitting some advice. So I thought I'd start with trying to go back to where we were in 1999 when we were thinking about FullCAM. It's a long time ago now, but you'll see as I run through this that a lot of the issues are not dissimilar. So we signed the Kyoto Protocol. We thought we were going to ratify very soon after that. Unfortunately, that didn't happen until 2007, which changed a lot of the plans. Really, what that meant was we had to start accounting properly for emissions and removals from the land sector, especially deforestation and reforestation under various articles of the Kyoto Protocol. And the diagram to the side shows the issue here, which was there was lots of work on forests and lots of work on agriculture and not a lot of work on the transitions in between that were now really important to us. The second part under the Kyoto Protocol was there were very, very few countries, apart from Australia, that had this exact issue. The vast majority of the developed countries were not experiencing large areas of deforestation and reforestation. And so we had quite a unique circumstance. We also had the unique circumstance of a number of data issues. We didn't have any existing inventory systems. And even if we did, we couldn't go in a time machine to go back to do 1990 baselines. We had no nationally consistent mapping processes. We had very limited access to data from the states. And what data we did have, for example, through the Resource Assessment Commission work in the 90s, was really focused on that productive forest estate, the taller forests that we think of, whereas most of the deforestation was happening out in the woodlands and brigalow areas. So that raised a whole lot of issues for us. I won't go through all of these on the Kyoto Protocol, but what the key issue was, we had piles of different guidelines, requirements, rules. All of these things had to be met. It was actually extremely complicated to try to even build the technical system that could report into these policy constructs. But the main point was always that we had to have consistency. It was vital to have consistency all the way through the time series. We couldn't be flipping and changing methods or results, because we had to know that our base that we were comparing our emissions targets to was using exactly the same results. The other point was that we were always ahead of the actual policy. So we were building a system without knowing the systems being what the policies actually were. So we almost had to over-engineer, expecting what might come down the track at us. And in many ways, that's still a problem today, although much of it's been much more locked in. This is a good example here, very quickly, of changes in guidelines. Exactly the same modelling framework, same results in terms of same input data, but depending on whether you decided to include various pieces of the land or exclude natural disturbances, you could get vastly different results. On top of all of that, the unique aspect of Australia's system was that we started to think about what were the other requirements for the system. So what did we wanted to look at domestic market mechanisms. So right from the start, we were thinking about how do we nest carbon accounts up and down through projects to reduce cost and increase compliance. Really thinking about scenarios, other data requirements that we were going to put forward. And this is what it really meant in the end. This table, for those that have not been heavily involved in the IPCC, may look a little confusing, but approaches are effectively how you represent and map your land, how complex you get, and tiers are how complex your modelling gets and how advanced your modelling gets. Most countries in Australia in the 90s were largely sitting in that approach 1, approach 2, tier 1, tier 2 style method. But where we really needed to get was into this approach 3, tier 2, and especially into the approach 3, tier 3 results. We can go into more on that in the quick Q&A if people have any questions. The result of this was really the technical criteria. So once you actually wrote all of those policy needs down, here were the technical criteria that we had to meet. And you can see some of them are quite complicated, especially back then. Small spatial units, less than a hectare, we had to be able to report annually. We had to do all of our pools. We needed to account for climate and weather. There were lots and lots of requirements that came out of those policy criteria. We very, very quickly learned that there was no quick fix or single solution to this. You weren't going to be able to just use remote sensing. You weren't going to be able to use just forest inventory or just soil sampling or just a process model. It was all going to be about integration. And the challenge with integration, as per this diagram, which is one of Werner Kurtz's favorites, is you have lots of different data. How do you actually put it together in a coherent way? And that's really where we started looking at FullCAM and the NCAS. So to get to the starting point, is to think about the NCAS. Now, no one talks really about NCAS anymore, the National Carbon Accounting System, but this was the system. The best way to think about FullCAM in many ways is just a component of the system. The NCAS had all of the data around it, all of the input data, all of the processes. That went into FullCAM as a modelling framework, and then the data came out and we turned it into policy relevant outputs. So NCAS was the whole framework and FullCAM was just a component of it. It's much better to think about it that way because then you can start separating the data and the models and the other frameworks out. And I'll go into a bit of that later on. But the core aim of the carbon accounting system was really to do complete accounting and forecasting for human-induced sources. That's a really key word or phrase there. Sources and sinks from land-based systems and an optimum response to the UNFCCC and its instruments. What I mean by instruments was there were all the trading mechanisms in there. So that sentence actually very neatly sums up all of the policy criteria that I just listed before. The concept, therefore, became to build a centralized and integrated set of national programs to support a spatially based, fully integrated, mass balance hybrid process model, FullCAM, founded on key national data sets. And that's really what we started building right away from sort of 1999 onwards. And of course, we had to have a lovely logo. I thought I'd put the old logo down there for the fun of it. Key development decisions in this that I think are really worth noting was that there was a really key decision to build that purpose-built system and to construct it around a single modelling framework. The main other decision was to do a progressive build by policy priority. There was no way we were going to be able to build everything at once. So we needed a comprehensive framework from the start that we could then start filling in later on as we started moving through as a 10-year, 3-stage plan, which you can see on the side. And so that was a very comprehensive plan. It changed obviously a little bit as we went through. For example, in 2008, when the CPRS was announced, a number of things got shifted around. But what we saw was a really clear pathway to try to get to that development base. We had multiple features of the implementation of the system. I won't go through all of these here, but the key part is that it was a continuum from research to production. We weren't trying to do research, we were adopting research, although we did fund some core research here and there. The system was always based on the design, so being offered just alternatives didn't help us. We'd already had the framework in place. Being offered a different framework was just going to cost more money and slow us down. So it was all about how do we work inside that single framework. We could be flexible, but it needed to fit within inside that. And then very clearly understanding all the different roles of each group. So where did government fit? Where did consultants fit? Where did scientists fit? And where did the private industries fit? And that made it quite a unique program in the way that it was run internally in government. Everyone was involved at some point. I think that's probably one of the key messages that I would put in here. Large areas of CSIRO right from the start and continuing through to today. All the state agencies, the Bureau of Met, BRS, ANU, lots of private contractors helping us on large components of the system. Everyone was bringing in, all in that sort of context of where did they fit in the system. So as a quick example of that, I thought I would start off with the remote sensing program, because this often gets a lot of interest. So you've got to remember that back in 99, 2000, there wasn't really any Landsat, large-scale Landsat programs. So the NCAS was the very first one. Landsat data wasn't free back then. So a really core policy decision actually was to say, no, we're not going to use MODIS, which is free because it doesn't meet the policy criteria. We're going to have to spend the money and buy all the Landsat data and process it because that does meet the policy criteria. That same process is going on today in terms of, obviously, Landsat and Sentinel are free now, but what about other commercial satellites, and where does that start coming in that decision process? But I'll leave that to the side for the time being. The main point I would make is that even the pilot program was 10 times bigger than anything had been attempted before. And so this was a huge program to build the amount of continental time series Landsat data over this space. To do that required really clear roles. We had government doing all the policy requirements. We had the researchers developing the methods and doing QA/QC, and we had the private sector and other government agencies doing the vast majority of the implementation to drop costs. That led to an 80% cost reduction from what was originally predicted. So really big advantages in driving that forward. The key institutional processes and arrangements, one of the main points that I think slips past a lot of the time is realizing that something like the NCAS and FullCAM are an ongoing program. They're not a project. They're not something that just rolls out after 3 years and you can turn it off, or you can just replace it. It becomes part of government reporting. So there's all of these questions you need to answer. You need to figure out where you're going to house the system, how you're going to work with other organizations, what are the budgets, how do you keep it going, how do you get staff, that are absolutely key to the resilience of the system, how do you retain them, how do you train them? So a lot of work on that in the background. With that, I'll start into the FullCAM parts. So hopefully that was useful as a bit of background into how we got here. So this is largely where we ended up. It's a diagram that shows we have land cover data coming in from the remote sensing. We have a whole lot of management information coming in from databases represented by the harvester there. Piles of different spatial information coming in, but all going into a core framework, and that was FullCAM. FullCAM then took all of that data, ran it, and dropped out these results. And that's what we're going to go into a fair bit more detail on for the next little while. So FullCAM is the framework. So it started actually as CAM4 and GRC3, which we built in Excel. So if anyone actually wants to get a good understanding of this, I'd strongly recommend just Googling, especially CAM4, and you can still download it from Trove and other old website areas. Really, really good place to start. It's actually just a replicate of CO2 fix, taken out of Fortran and coded into Excel. The issue there, of course, is that when you're trying to run lots and lots of areas, Excel's never going to work. So it's an excellent test bed, but it was never going to scale. So FullCAM became the scaling piece. It was developed by the NCAS for modeling the carbon and carbon stocks and greenhouse gas emissions and stock flows. It integrated lots of models, but really the key part of it was how did it integrate the data and how did it bring the data together and how did it operate spatially and temporally and allow us to move between those land uses, going back to that deforestation, reforestation issue. So the best way to think of FullCAM is a shell with lots of data that gets fed into it. Lots of models went into it. So when we started talking about FullCAM, everyone sort of said, oh, it's a new model. We're actually quite clear that it wasn't. It was actually a coherent linking of existing models. So these are all of the models that we coded into it over time. So CAM4, which is really important, we'll go into more because that allowed growth through a mixture of options. So it allowed it through the tree yield formula, which we'll also go to, but also inputting just yield tables, volume yield tables, converting out of those, or inputting above ground biomass tables. So there are lots of different options available in there. And it also managed all of the different pools and products. CAM-Ag, which is effectively a replicate of CAM4 for the agricultural sector. The Forest Productivity Index and the tree yield formula, which we'll go into a fair bit. We did write 3PG into the system, but we never updated it from the original Sands and Landsberg version. There are a series of debris decomposition models that you can switch on and off, and turnover models that fed those. A couple of versions of Roth-C for soil carbon, but the main one was always run at 26.3. GenDec for mulch decomposition, if you wanted to turn that on. Interestingly, right from the start, GORCAM, which, as Patrick referred to before, really important, was looking at bioenergy and product displacement. What's the benefits of using timber over concrete, for example? Economics and log volume conversion models. We did put an end cycle model over the top of it, although that was never fully tested or run. And it had a full Monte Carlo sensitivity and semi-optimization routine written into the back as well. So quite a comprehensive set. The main thing is you could switch these models on and off depending on what you wanted to do. You could also switch them on and off through simulation processes. So you can actually swap between various models as you were going across the landscape. Very simply, that's the framework at a very high level. It's not unsurprising. It's a pretty standard carbon flow model. Anyone that's worked in this has probably seen something like this about 1,000 times, with carbon coming in from the atmosphere and then moving through debris pools, product pools, soil pools, and leaking effectively back out to the atmosphere as carbon decays through that process. FullCAM worked by having I still believe works by having two replicate systems. So there's a complete forest system and a complete agricultural system, but then they report together, which allows you to do those transitions between the land use, especially for soil, for example, where you're clearing forest and the soil decays after that post. And that's a really important point that we're going to come back to, and Geoff's going to touch on as well, around the impacts of how that works. Looking at this diagram, the key thing to remember is that if something goes wrong in a pool, for example, the soil pool, it typically means that it's not an issue with the soil model, it's a model above it. It's something that's feeding it down. And so you can actually, if something looks like it's going skew-if, it's often happening 1, 2, 3, or 4 levels above where that is happening. And then that's flowing through the system to cause the problems down the track in a mass balance framework. That's really handy when you're actually testing these systems. That's just a diagram, much more complicated. Same thing, but just shows all of the pool structures. And all of these are available in those Excel sheets I spoke about, the GRC3 spreadsheets, if anyone wants to see all of the detail of that eventually. So now we go back to some old slides. This is the first one's FullCAM as of 2008. It was all developed in C++. We were desperate for speed. Compute power was certainly a major problem for us in the simulation process. So everything was about speed. We had a GUI interface, multiple simulation options. It was quite a large executable for the time. And that pile of paper there is it printed out in about 2008. For some reason, we were requested to print it out for some odd government purpose. And that sat on our desks for quite some time before we probably just ended up putting it in the recycling. The key other parts of it, though, was really designed to be fully operational and really reliable. So there was piles of work put into the full regression testing frameworks so that whenever an update was made to the system, especially in the code, it had to make sure that it matched previous results unless there was a reason for it not matching previous results. So it gave us full confidence that we weren't accidentally breaking any code or algorithms at any time. And that helped ensure the mass balance as well. There was also extensive error checking processes that were built in around the back of it to make sure that results weren't drifting or changing too much. Everything was built to fit within frames. There's a detailed release and code management process. The GUI probably looks familiar to anyone that's used FullCAM. It was designed in 2001, 2002. It's had limited updates since in terms of just how it looks and even the tabs, even on the web forms. It's largely the same. There's 4 types of plots within FullCAM, and I think most people would be familiar with plot files, which run point-based models. Most people would be familiar with estate files, which allows you to sum those plots up into an estate. But the spatial files of how you actually run spatial analyses and the database files of how those fit, they're actually only held within the department. And so probably not particularly familiar to people. And I'm going to go through that, how this works as a process to try to get you that understanding a bit more. So how does FullCAM work conceptually, spatially? I think is probably the main point is what I'm going to try to cover here. So everything for us to start with was about, firstly, did something change? And if it did change, we needed to know the type of the change, the time of the change, and the location of the change. And this is where the remote sensing program came in. So you can see that this is very much out of date to some degree, but the same process remains. Full Landsat running at roughly 25 meters. At the time, it was 15 continental coverages. It would be well over 30 now. And that's obviously getting updated in the near future by CSIRO over in Perth. We had a very strong focus on getting 1990 right as the base, and then also getting the 2008 to 2012 periods correct. So lots and lots of focus on making sure those were accurate, but we've needed the time periods in between to make sure that we were tracking age classes correctly. And importantly, allowed us to move our transitions backwards and forwards over time. So I had the mapping and modelling, monitoring at a continental scale, that then allowed us to identify the timing and location of an event. So what you can see here is some high-res imagery, the underpinning Landsat, and you could see the changes, and we could actually then date the changes as they went through. And that allowed us to say, oh, it was forest. Oh, now in this year, it's not forest. That's a really good starting point. Or it wasn't forest, and now it's forest again. And this is an area of a chunk of West Australia at the time. We applied a process through CSIRO developed the probability network that allowed you to gap fill over and through clouds to give you a consistent time series. I won't go into that, but it's still quite a remarkable process that was applied, especially to give us these time series rather than these sort of 5-year chunks that you saw in other areas of the world. And reforestation was a bit different. We had 3 classes. So originally we had forest, non-forest, and then when we went to reforestation, we split it into conifer, hardwood, and other native. Primarily, Landsat couldn't really determine between the conifers, for example, but we had other methods of doing that, which I'll get to. And so we didn't need that. What we just needed to know was it a conifer plantation? Was it a hardwood plantation? Or was it a native forest? So now we've got our location and our point of our time of where it changed. Now we need to go and get all of our site and climate data. One of the most remarkable pieces of NCAS in many ways in the early years was building the monthly surfaces of climate, the 250 metre and 1K grid across the country. That had never been done at that scale before. Jen Kesteven from ANU led that work. Absolutely remarkable what she managed to pull off in that time, given their compute power. And more importantly, she also spent 6 months fixing all of the historic climate records for the country, where people had incorrectly entered data in their climate records, and that had sat in the systems for decades. So she had to do a massive cleaning process before she built these surfaces. It was quite an incredible achievement for the program. Lovely animation at the time. This just shows rainfall, for example, monthly running over the country. Always loved 1974 for those that are interested. That's coming up. There we go. Very, very wet. Really fascinating period. We had an initial soil carbon inventory just built from existing data. It was good enough for what we needed at the time. And these data have been improved since, obviously. But there was a full carbon data map underneath for initial conditions. There was a maximum biomass surface. This is the original one. It's since been updated. But basically, the concept was to build a relationship between some indices and what we thought a site could reach at its maximum, at maturity or past maturity, when it was in a largely undisturbed state. So the main purpose of this map was to give us a starting condition for forests that existed, or a potential condition a forest could get to if we saw one coming up. And then the remote sensing helped us tell how long that forest had been there or not. So we combined the surfaces with the models to get to that point. We used a tree yield formula, which I'm going to go into in far more detail in a little bit, but it basically allowed us to produce a sort of a hybrid process model for forest growth with a simple formula that could actually be really easily modified, and you could kind of make it fit anything, which has advantages and disadvantages. And that's another point that we'll cover soon. The productivity index went through time. So it meant that we could actually account for those weather conditions across the country as we went. And here's some examples of some tree ring data that we did with Matt Brookhouse, actually, across some of the native estate, showing a reasonably good relationship, actually, between the FPI average as an index versus what you saw in your tree ring widths. So we've got all of that data. We then need to know what happened on that site. And this is where the databases come in. Now, this is a really important piece that's often sort of looked over in the FullCAM story, because databases are kind of boring. But actually, these underpin exactly how the system operates. So what the databases were designed to say, well, there's lots of things we need to know about the land, but we actually can't get spatially. We can't get it from Landsat, or we can't get it from a satellite product. especially going right back in time. So what do we do instead? So we have a series of databases that look up what might have happened in that area. So a really good example of this would be if you're in West Australia, for example, and we see conifer come up in that remote sensing product, we need to say, well, it's conifer and it's on a sandy soil and it's in this rainfall zone, therefore it's pinaster. So we'll try to use logic trees to then feed that back. And then we can say, well, it was pinaster and it was planted in this year. And so therefore, here's how it was managed. So when you look at the toolbox that we'll come to later on, and that many of you have probably interacted with, and you click and it gives you a series of management regimes, they're coming from that database. That's how the system was built. All you're doing is just short-circuiting that process as a user. I won't go into this too much. There's a full paper on this, but it allowed us, the databases, to say, move between land uses, changed harvest types, changed the way that forest regimes were included. And also because we were never sure exactly what regime might be going forward in the time, we could allocate those randomly across the landscape within that region. So at an individual pixel, when we were running spatially, there was a pretty good chance we'd be wrong on the management regime. But as we came out of the system and came further and further out to a regional level, that would get more and more right, basically. And that was just an assumption there. But again, on the project level stuff, you just got that point. The key aspect for FullCAM is to think of it as an event-driven model. Everything happens because of events. And that's relatively logical. So they change the system state, and everything has time and parameters attached to it. There are piles of different events in the system. I won't run through all of these, but when you look at them, you can see it. And all changes, where the carbon stocks are, it moves carbon between pools or out to the atmosphere, or it impacts growth immediately or well into the future. We have the same for agricultural events. FullCAM then built event queues, so effectively a regime. So this is an example for Nightons in Tasmania, where there was assumed that it had been running as agriculture for 18 or so years, which are the yellow ones. You can see it was ploughed, then it was cropped, then it was grazed, and then it was converted. So you can see a cultivation strip plough, a weed control, then a conversion to trees, and then a forestry regime after that. And those were all held in these databases, and there's a lot of them, and they're spread across the country. At that point, you then model the ecosystem for that point. And here's some example outputs. Is a Pinus radiata output from South Australia, assuming a 4-thin system, which we know obviously doesn't really exist anymore, but that was one example that was in there if you put it in, for example, in the 80s. And you can see exactly what's happening in the model. You've got the green tree, you've got the soil carbon declining from the previous clearing and the cropping. It then grows to trees, the green line. You then, at every harvest, start getting debris. That debris decays. You're taking material off as products. You have a land clearing one in the middle, trees sitting there, trees get cleared. Then that nice red dot there or spike there when the debris all gets burnt 6 months later. And then you have a slow decline in your soil carbon. And this is an example, the second one of a cropping in agriculture where you've cleared land and you've just heavily cropped it and the soil carbon has declined. So all of those things come together in the one system. Then you just sum it to the account. Pretty simple, though very, very horsepower intensive. So 25 meters being run monthly across the entire country. Back in the day, it was about 30 computing days for a single simulation. So we had large challenges with running this. We had to buy compute clusters. We were often running multiple laptops. It was not a simple process. It certainly wasn't cloud-based at the time. And this just allowed you to see, this is another example of looking at the emissions over time coming through the process. So with that, these were the advantages that we had. We had a bottom-up approach, some mass balance modeling, and some transitions going on. This was the most important part of the system. We really aimed to be policy independent and then give structure and development to the enhancement activities. So we weren't trying to build a system and then throw it away to build another system to throw it away to build another system to throw it away. That was the really key aspect. We were trying not to do this stat collecting of, we collect enough points, don't worry, our model will eventually work. We were trying to have a framework of saying, no, we've got a framework and we're going to collect data inside that. I'm not sure how many questions have come through, but if there's anyone has some questions for a few minutes, we're very happy to answer those.
But if you do have questions, if you don't mind popping it into the chat.
Why can't planting stock be specified? That is an excellent question. It was specified in the original toolbox. It was not done specifically by stocking rate. It was done by changing the initial growth rates of the forest using type 1 events. So it was allowed you to choose between a lower stocking, high stocking, and direct seeding. I'm going to cover that a little bit more in the modelling component around how that works.
Just on that, I suppose there's going to be a theme throughout this. What we're trying to do is explain a lot of the policy settings that FullCAM was developed and to why, and then into the specifics of how that model can be changed going forward, which can feed into the AFWI discussion about research priorities. But you'll consistently hear us saying it's a very flexible modelling framework. So questions like that is a great one. The modelling system can deal with different stocking rates, and there's different ways of dealing with it. At the moment, that isn't being applied, but that doesn't mean the system needs to change. It may be that the calibrations need to change. And that's sort of what we're keen to understand about where people's pain points are as well.
What are the key differences between the forest system and the agricultural system on cleared or heavily grazed areas? The soil carbon model is exactly the same. The debris pools feeding it are slightly different because they're coming from different plant components. So what you have is obviously trees are quite different to grasses and pastures, and even grasses and pastures, you've got great differences there. So realistically, it's the plants that are feeding into slightly different debris pools that are decaying through. So as Geoff said, again, the system's quite capable of doing this. It's actually a matter of, especially in those heavily grazed systems, how you feed that model in. And a lot of the modelling results, for example, for plant growth aren't directly fed into, actually in the model, for example, they may be fed externally from spatial surfaces. That's a great question, Dean, and we're going to go into that in the future. The science on the data and calibrations has certainly progressed. In terms of the framework and the core concepts of the carbon cycle, we've both kind of been there for quite some time. So it's a matter of really thinking through the components of the science. And that is something we're really going to touch on later, is that you need to be very careful when you're playing with this model, because if you play with one piece of the science and then you change a parameter in it, thinking you've improved it, you very often break a number of things down the line and cause really odd results. So the answer is yes, the science has, of course, moved along a long way, but it also, the core concepts of not, is 3PG no longer available for tree production? To be honest, I haven't checked whether 3PG is available in the tree production. Even if it was, I would be inclined not to use it because it is a very old version of 3PG. When someone says they've used 3PG, you don't really know what they mean because there's so many versions out there. So if you were to use 3PG, for example, at the moment, probably the best option would be to run it externally and drop the results into the yield tables in FullCAM itself. Duncan's got a fantastic question, which we're going to tackle later, because Geoff and I are both working on that issue at this very point in time around how do you bring new measurements at the project level and have them integrated. That's really a role of the department. It's not really us as such, but there are multiple ways of doing that. And that was conceptually included in the early releases of the toolbox. As a quick recap from that first section, I hope what people got, and of course, I'm very happy to answer the questions here, is really understanding that we were faced with some very, very complex new policy criteria. And it wasn't just about sending a spreadsheet to the UN every year. It was about how do you actually enable the land sector to do its best for carbon in particular, and how do you let it scale, and how do you support market mechanisms, and how do you support policy implementation. And when you listed all of those policy requirements together, you ended up with a very detailed set of technical requirements that needed to be met. At the time, of course, there was no data or systems. Even the original deforestation numbers in the 90s were largely developed off estimates of diesel use by bulldozers. And then that was back converted to how many hectares a bulldozer could clear. And you would then say, well, then on average, a hectare has this. It certainly gave a number, but was certainly never going to support ongoing policy. So really, the key aspect of FullCAM is that it was a policy-led tool. It was a tool that was built for a specific purpose. And everything had to continuously refer back to what are we building this for? What are the actual needs? So rather than a science tool, very much a policy tool that drew on the best available science and could be improved through time. So with that, I'm actually going to go into the National Carbon Accounting Toolbox and then a little bit into the models before we hand over to Geoff, because we're getting quite a few good questions through, and I think we're going to need a reasonably good Q&A session here. So the National Carbon Accounting Toolbox. This was our first attempt to release everything that had been done in those 5 to 6 years up to 2005, 2006. A lot of this came actually from what I was discussing before in my early work for the Greenhouse Office in Bush for Greenhouse, where what we had very, very quickly realised was that if you tried to do pure measurement, especially in environmental plantings, then the cost of doing that measurement to any sensible degree was going to be so high that there was no way you could actually make any money off these carbon units. And so we had to go down a different approach. We had to go down a deeming style approach. And that was where the toolbox had really started to come together at the time. The aim of the toolbox was therefore to release all of that information and try to build that initial process for using this in carbon markets and reporting. It had 3 key components. It gave access to FullCAM. It had all of the NCAS technical reports in the background, and also the whole data viewer, which allowed you to see the remote sensing products. So I'll go into those a bit. So the data viewer these days would look extraordinarily outdated. It came on a dual layer DVD, which back in the day was a huge thing. And it had 5 of our 15 Landsat continental coverages from 1972 to 2004 that you could look through just as images. It included all of the maps of that rainfall, temperature, and evaporation. You could also load it up into a GIS system via a mapper. It obviously had a number of limitations. It was really just a viewer, but it was the first time that you could look anywhere in the country easily and look back at time and go, oh, I wonder what happened there. However, of course, we had huge volumes of all of the other data that we'd produced, especially all the Landsat data that had to have been sort of from the raw data processed all the way through to analysis ready. And all of that at the same time was made available through Geoscience Australia. So those remote sensing products really formed the basis for multiple other pieces of work going forward. The technical reports was probably about 45 released by 2005-06. We only did about 3 or 4 more by 2008-09, and that process has largely ceased. But I would highly recommend anyone that's interested in FullCAM and the backing information to go and actually find them and have a look at them. They stack, they're huge. It covers everything, all the soil carbon models, all of the data that was collected. If you're looking for basic density, for example, for tree species, there's an entire report on that with an Excel sheet with hundreds and hundreds of basic density values, all collated. It was a massive effort to go out to all of the universities and drag together all of the existing information that we possibly could to build the system, but then also document that and make sure that it was actually available. Really, really key. There's a couple of really important ones in there. Very hard to find. If you type in NCAS technical reports, you'll find the odd one, but you can go back to the Greenhouse Office website on Trove, which has been archived from 2007-08, and they're all sitting there, along with CAM4 and along with a lot of other resources. So you can grab that link later if you like. The FullCAM data builder was really what the toolbox was focused around, though. So we had FullCAM, we had the framework, but the big problem with all of these models was how do you fill it with all of the data that you need? It's horrible. There's hundreds and hundreds, if not thousands, of pieces of parameters, variables, et cetera, et cetera. It simply wasn't scalable. So the data builder allowed you to, we put all of that spatial data onto a server. It allowed you to enter a lat and long, click download data, and it pulled all that data off the server and dropped it into the app. First time ever doing a web-enabled app like that for carbon accounting in the world. That you could build those plot files, you could save them, you could rerun them, you could modify them. The idea was to provide the entire framework. So we weren't trying to cut pieces in and out or restrict access to it. You could do whatever you like with it to get the results that you wanted. We also provided a series of validated benchmark plots with that allowed you to look at your results and go, oh, I changed this number, it looked a bit silly. And you could check that against those benchmark results. That's really the toolbox. At the time, these were the groups that were using it. We were running it through Greenhouse Friendly. We were running a lot of it with the Greenhouse Challenge and the Greenhouse Gas Abatement Program, for those that can remember back to those policy programs. And we did have a number of users using it as well across universities and NGOs. And CSIRO, as a mix of users, as a user of it for the sort of the consulting style business, but also continuing to develop the system for us, especially on the soil side. So lots of different versions of the system. The aim to release it, again, was all about policy. We wanted to make sure that there was a quality assured model framework that people could use, so that you didn't have to go and have your Excel sheet audited every time you needed to release some results. And that was a common problem that we were seeing with some other groups that were just building things in Excel, and it's continued since then. So how do you make sure you can say, look, here's a framework, they've used that, now you only need to check the input data, and how you would analyze the outputs. You don't have to question whether all the maths in the middle's been done correctly. We wanted to give the best available data as the national account had. We wanted to really also give access to all of this data, and especially the climate that we developed, because we just saw it as so useful for multiple other purposes. And then really starting to look at how do we reduce these costs? How do we test what if scenarios? And how do we actually start to build a user community? And that was a really interesting challenge at the time that hopefully we might have some questions on. But building that user community was really important in the early years. It was about making sure that people understood how the system works, so they could then interact with us to say, oh, we like this or we don't like this, and how can we improve it in the future? So that was the toolbox. Now, I'm going to go briefly into the data and models, but in particular, just the forest side of what backed all of the toolbox in at the time. I'll put up here one of my favorite cartoons about carbon models. So you make sense that I have a general feeling on this, which is that this is what we typically see across this space of lots of model comparisons and model discussions. But again, that's very useful science work, but how do we actually fit this into a policy framework? So how did this all actually work? So there was, first of all, there was a huge amount of effort to bring together all the existing collating all the data. And I said that's in the technical reports. One of the bigger pieces of work actually was that all the data had to pass checks. So it wasn't just we will grab the data and put it in a database and use it. There were really thorough checks on, does this data make sense? Does it actually fit the criteria? For example, are the plot sizes appropriate? Is there researcher bias in the results? Are there other problems that we've seen? And that was all done externally from us for independence purposes. But even though we had huge volumes of data, a lot of it in the end just turned out not to be suitable once we actually checked it. The vast amounts of research did get funded, especially in the remote sensing and the soil carbon, to a degree, the forest modelling, and especially the climate data, and obviously doing all of the modelling framework. The main thing we were trying to avoid all the time was large stratified data sets that created anomalies. We didn't always succeed at that, but by that I mean where you would have just big clear lines of, say, over X rainfall or below X rainfall, because then when you crossed a boundary, you created these false lines in the system. And so everything was about trying to look at surfaces. How do you make surfaces? And we talk a bit more about that later. This was the core design of the growth model. So we looked at multiple different growth models, everything from process models through to really simple, just using empirical yield curves from different research projects. In the end, we tried to land somewhere in the middle, because what we needed was something that we could apply spatially in areas where we didn't necessarily know a lot about, but they had to be in the national account. And that we also wanted to be able to consider climate to a degree. And we wanted to really be able to reward good management as well as you were going forward in the process. So with Chris Brack from ANU, we implemented a pretty simple model, single inflection curve could be modified on multiple factors. So we had the maximum biomass from the maximum biomass layer. So that basically set how much biomass you could get to at a single point in the landscape. This is a 250 meter grid, and still is. It gave you a point of maximum increment for that curve. So how fast do you hit that maximum over time? Well, not quite get to it, obviously, but get right up next to that. Lots of different curve shapes in there. And that was set off an idea of what's the age that your maximum biomass occurs at with no influence of any other factor. We then included those two things are great, but they don't allow you to do too much. And it makes the model quite inflexible if you only play with M and G, those two parameters, or even both of them. It still keeps it it's quite inflexible. So we started adding additional factors that allowed us to move the age of the forest around. So we could start to say the effective age of the forest is older or younger because you've applied effectively a type 1 effect. That is that the growth increases, but the maximum doesn't, or a type 2 impact, which is where the maximum increases. So we put all these different effects in. So we had adjusting effective age. We had a species adjustment called R, which said if you plant this species on this site, for example, pine, it will grow different to the native forest that M is predicting. So that applies over the entire period. We also had another multiplier on that called Y, which you could apply during a rotation. So if you were growing along at a set thing for a species and you put a whole lot of P on it, for example, and you showed a big growth increase and that was going to go through the entire rotation, you could lift at any point. So the idea was to give you an ability to move the model around through time, depending on how you were managing it. And then we also added a biomass adjustment that allowed you to move back to the effective age of a forest. So if you were growing up and you cut something down, you went back and you could keep regrowing that, which is a pretty standard sort of process that countries like Canada and others use in their systems as well. So pretty simple model, actually, but very, very flexible, which was one of its key components. The PA on PAB was really just to try to look at how the climate impacts the forest growth. So you had the productivity over a period versus the average productivity, and that would modify the growth. Now, if anyone's looking at this equation, you can probably see a small problem with that, which is that it's sitting on the outside of the model, whereas outside of the multipliers, it probably should have been inside the age component because you hit some problems because of the way that component's there, but it didn't impact us at the time, and there have been some changes to that since. So here's the high-level growth concepts just as figures. So you can see a couple of things here. You've got a standard curve, which is just growing away in a solid line. You can see on that first graph around age 10, we've applied some modifiers here so that the growth's been exactly the same. And then we've added a type 1 effect, for example, and it starts to pop up. And so you're changing that growth partway through, or you could apply effects all the way through the system. The graph on the right is showing the CAI curves. The important part with this is to remember that when we were trying to think about this, we were going, well, we are assuming that maximum biomass occurs roughly at canopy closure, or that maximum biomass, the age of maximum biomass occurs roughly at canopy closure. That could be considered as the G number by just moving that around. But the problem with doing that is that as you pull G over, you vastly increase the growth in the early years, and you can get very high numbers very quickly. So realistically, that age is actually the impact of G minus the type 1 effects. And so we were trying to use type 1 effects to pull those curves back to say, yes, we'll get more growth and the age of that maximum growth will occur earlier, but it's not actually going to really increase the peak of that growth. But you could increase the peak. So they're basically trying to be super, super flexible on how we adjusted that. A really good example of this would be pine plantations. When you were thinking about the early growth as things like the maximum growth sequence started happening in the 70s and all of the impacts of improved management through the 80s and 90s to get the trees off the ground much faster. So you were front loading your growth in those early years, but you may not have hit a different maximum actual increment point. You just moved the curve back a bit. So that was the concept being applied inside there. The environmental plantings side, so we have two components effectively. The environmental plantings, we just ran an assumption they grew at the rate of a native forest in the M layer. Reasonable assumption in the given the complete lack of data on that, which is probably the biggest move forward in the last 10 to 15 years, is that we finally have environmental plantings of a sensible size that we could measure. Even back in the 2000s when we were trying to measure them, there were very few around. And the ones that were there probably weren't very representative, probably a good way of putting it. The idea then was you could also modify early growth based on management, so you could reward good practice with a type 1. So you could say, yes, I did really good weed control, or I did put in some FERT, for example, and I front-loaded a bit more growth. So you could bring those things back. We had looked at additions of type 2 impacts as well, in terms of saying, well, yes, that's the average for the block, but what if I was planted next to a stream site or other things? And those never really moved forward at the time. Plantations, slightly different. Still use the underpinning M layer, but was calibrated differently to a species region and a rotation length. And I'll show this on the next couple of slides, but it was locked to known growth ranges. So without trying to be too critical here, one of the challenges was we were trying to reach out for plantation data in the 2000s. We were consistently being given look, we'd love to work with you, but we're not releasing any of our results or data. So the data we had to use to build this system. The idea was to make sure that the results for any given region would fit within the known MAIs of that region, so that we could make sure, and it fitted standard growth curve shapes. So that, yep, we'd certainly be wrong at a point. We were never trying to say that this thing was perfectly accurate, because if it was, well, plantation companies wouldn't need models anymore. But it was just trying to make sure that we fitted in that range. It had a huge range of species in it. And we really worked hard on getting some key components in there, like the time series allocations, which are absolutely vital for getting your wood products correct, and working on time series density. So I'll show a little bit of that as well. So this is an example of the plantation model. If anyone ever reads the paper that we wrote on this, you'll note that in the table, it unfortunately auto-corrected everything to eucalyptus globules for some reason, which is still one of the larger embarrassments of my publishing career, and I can't help point it out. But what we did was we calibrated for every specific NPI region, because they were not, we couldn't run a single plantation calibration for a species over all of them. They just simply didn't match. And so we needed to do this region by region by region. And the way that we did this was actually quite simple. We had our maps of, for example, all the existing pine in a region. We took that, we put that over the top of the FPI range, as you can see here. So this part here was for the green triangle. We knew here's where our softwoods and hardwoods were. Here was the distribution. We gave the low FPIs, say for pines, 12 to 14, depending on the region. You got the highs somewhere between 26 to 28 to maybe 30 if you were doing really well. And we sprayed the results across that for the MAIs. So what that meant was that the mean was always going to be the same, and it would always be consistent with plantation inventory. And again, we were locked to those known growth rates. We then set out a pile of other processes, and I touched on that, IPCC root to shoot ratios. So we set different root to shoot ratios for different species at the time. This was pre some of the papers that were coming out saying, we'll just make it 1.26. That's fine as a multiplier. So I think it was 0.2 for pine and 0.25 for eucalypts. But those were just baked into the system. We had basic density time series for commercial species, primarily eucalypts and pines. That was really, really important, because when you're thinking about FullCAM, it's back calculating from biomass down to stem volume. And so once you know your stem mass from your biomass, which I'll get to next, you need to know the density of that wood so that you can understand the volumes and compare it to your yields off the table. And that's this graph down the bottom here is directly from a pile of work that Peter Snowden did, collating for pines, in this case, the basic density functions. So the challenge there is that a lot of people say pine, for example, is 440 kilos per meter cubed. Yeah, that's kind of true at age 35 to 45. But if you're cutting out thinnings at 10, 15, 20, 25, or even now earlier trees at 30, that's not true. And so it had a really big impact on the way the calculations were done for those volumes. Really important to have that in there. We also did the allocation to plant components through time. So this is the graph above. The graph looks wobbly, but there's a really good reason for that, which is that this is actually allocation of points in time, and it changes at the time of canopy closure. So it's not meant to actually look smooth in the model. But what you can see here is a pretty clear process where very early on, there's very little stem as a proportion of the total mass, but very quickly that starts to build. And by the end of a rotation, you're getting up towards, sort of 80% every year of any growth is going into the stem. And again, that's extremely important when you're thinking about thinning and harvesting through that period, because as you're removing your stem wood, it needs to be the correct amount, and it changes everything. It impacts the litter debris, it impacts the soils. So a lot of processing that. All the debris numbers were generally just checked to be known within ranges. Debris is always very difficult. Again, there's the technical reports. The same with soil carbon. That was never really released or talked about for the toolbox, even though the model was there. But generally, the idea was that it should stay pretty flat. It'll move up and down a tiny bit. And if you started to see big movements, then you'd be having challenges. So this is a graph I've just quickly put together. And you can see here, if you look on the left-hand graph, The green line, hopefully there aren't too many colorblind people, I'm afraid. The green line is a yield curve for the region that we're looking at. This is actually ACCU flows. The blue line, the solid blue line, is the 2016 FullCAM run, which is kind of roughly showing a similar shape to a degree. And then the dotted blue line at the bottom and the dashed line at the top of it are the ranges that you would see in this region. So you can see the mean, you can see where it could get to, and you can see where it could go down to. And the model's basically locked around that. I won't go into this. Geoff can go into it a bit more. The orange lines are the 2024 FullCAM and 2020 FullCAM effectively. So you can see really a huge difference there in terms of the way that the curve shape works, but also the MAIs that you'll get out. The graph on the left is another example. For example, you see that green line isn't trees, that green line is soil. So this is a good example where you could look at the results and start to say, gee, well, there's clearly something wrong in the model because soil should be pretty flat. So the trees probably look fine. So what else is happening as you're flowing through that system? And these are results out of 2024 FullCAM. 2020 FullCAM. So this is what you can see in the system as you're looking through it and just thinking all the time, well, those results don't quite make sense. Why don't they make sense? Well, it's something happening up here. We did lots of validation and verification. My favorite sites is 10 of these now, but I do like to focus on these for a really interesting point, which obviously isn't overly published. These are spotted gum forests on the south coast. If Fabiano was here, he would be able to give me far more detail on this. This is where it cleared full half-hectare areas and weighed every single tree, which meant there's very, very, very few sites in the world where that's ever actually happened to allow you to truly test an allometric equation. And so one of the most interesting analyses of here, in this table, is that if you look about building those allometric equations from these sites and then applying them to the same sites. Now, this is a much broader discussion, but I would encourage you to look at the percentage error of, for example, taking the high quality site equation down the bottom and applying that to the low quality site, at which point you will get approximately a 35% overestimation of carbon that you would not have detected. And that's a really interesting challenge in this space as we start talking about measurement. What are we actually measuring? Lots of bits and pieces on these. These are mainly out of technical reports and papers showing how we calibrated the soil carbon models. Again, one of the big challenges for a lot of these models is that there isn't actually a lot of data available for them, which is a really big challenge. So to get a soil carbon model to work, you really want to be measuring all of the pools and all the stocks and fluxes that are moving so that you can understand what's happening. Not a lot of those sites around Australia. And that again comes to an issue of what are we trying to measure, which is probably the topic of another discussion. Like, what are we trying to measure? Why? And what's that measurement actually going to tell us? And that's a really big challenge in the carbon space because there's a lot of measurements being taken. The question is how useful are those measurements going to be to us in the future? And that's a pivotal question that the industry hasn't really addressed, in my opinion. That's a fantastic map that shows up on my screen and isn't showing up on yours, unfortunately, but it's really just showing a verification process at the time for the remote sensing. We did lots of work with, at the time, Iconis, which was considered very high resolution then at 1.5 meters. Remembering Landsat was seen as fine resolution at 25. And it gave a sort of trying to check the results all of the time. So with that, I'm going to just do a sort of a 10-minute, I guess, lessons, issues, and thoughts around all of this from my side. And of course, I'm hoping I'll hopefully get challenged on a number of these things. I'm assuming Geoff's watching all of this happening. So, but I'll try to raise these points and see where we get to before I hand over to Geoff after a short break. So where were we in 2010? 2010, we had the spatial modelling frameworks running. So deforestation, including the regrowth, the reforestation, the plantations. We had croplands and grasslands running as well. All at different strengths, I would argue. It's not as if everything was perfect, or certainly not trying to claim that. We had estate modelling spatially referenced for native forests and sparse woodlands. We had some other models running, non-CO2s from fires, economics. We had interface and usability issues. So there had been a large push to develop a online spatial MCAT as part of the carbon pollution reduction scheme that had really pushed very hard from 2008. Unfortunately, with the end of that scheme, there was a push just to fall back to, along with a lot of other stuff that was done as part of that, to fall back to the 2006 NCAT. And that's largely what's still there. So I'm going to put down a few lessons that I learned through all of these years that hopefully are useful. So the challenge with all of this on the policy part has always been, are you oversimplifying or are you overcomplicating? The system has to be as robust and able to meet all the reporting requirements. And the key word here was always robust. The cutting edge science was great. We're very supportive of it. We wanted it to come through because it would improve the system in the future. But if we couldn't robustly and routinely run it or use it, then it became a challenge. Think about remote sensing. A good example was Pulsar, the radar satellite from the Japanese Space Agency. Looked fantastic, could have really helped, but then it broke and there was no replacement. So the big advantage of Landsat was that we had continuous coverage and we had the ability to know that that was going to keep coming and that the US was going to keep firing Landsats up. So really making sure that we had robust systems. We needed to define what simplicity was, and that's a really important concept. Is it the concepts and understanding that need to be simple? Probably. Most of the concepts and understanding that were put out today are pretty simple, really. The management and operation and the models and structures, they can be quite complicated. It just needs to be in the background and have people who know how to run it, obviously. Policy requirements honestly just never made these things simple. And the big problem with inappropriate simplicity was, do you discount, or more importantly, you build something simple and then you need to throw it away and start again? And if there's one lesson I probably haven't put up here, as I learned, is an interim system becomes a final system very, very quickly. And then it's very hard to move on from that. So the system should be as simple as possible, but not more so. Mass balance really, really helps. So I know we focus a lot on the trees, and quite rightly, because we're all working in forestry. But as you start looking at debris and other pools, if there's an issue in a pool, it's invariably driven by the pools above. And that's a really important point. It really helps you look at the model results in a much more coherent way. Now, I know we've got people like Belinda Medlin and others on here who would be able to talk with much more detail about this. But the key is that you're always checking all of those pools, and that you can't change little pieces of the model without considering the whole model. If you change a parameter or a growth aspect of the model or something, the turnover rate, for example, to try to get the debris right, there's every chance that you could actually also break the soil down the track. And so you must be working always and testing the models spatially. So you're not trying to find an average, you're trying to find the full spatial distribution across a landscape. If you just try to find averages for regions and see that seems to look okay, well, what you're going to find is the extremes are often wrong. So how do you make sure that you've always got these checks spatially and temporally? I think from an operational perspective, my biggest lesson in all of this was definitely about framework research. So how do you get the research to work within existing frameworks? So NCAS, how do you get it to work within the policy frameworks? How do you get it reporting within the reporting frameworks? Now, at the time, these were just the UN and the emissions trading systems of the voluntary schemes. But now it's all about, potential use for voluntary reporting standards. It's getting very, very complicated. So there's a lot of reporting frameworks out there. Really targeting your research within the framework. So the big advantage of the framework in many ways was be able to say, well, we know all these parameters. We'd run Monte Carlo over the top of it so we could see what the most sensitive parameters were, so that since we only had limited budget, we would throw our money at trying to work on those parameters. We wouldn't throw our money at the parameters that were far less important. So it really allowed us, with our limited budgets, to do that. It also meant that if we did get buckets of money coming in, which now and then happens in government, we could immediately have a thing of like, oh, we can go fund this. That would help a lot. So really helped that targeted research. We still did a lot of non-framework research, especially in the soil space. It's still important, but it was really as a future path. It was how do we move forward in 5 to 10 years? And then really aiming to prevent the duplication of frameworks. That the last thing we needed was 7 frameworks all running off the same data and then arguing with each other. Hopefully by the end of this, I've got 2 slides left. But the main point I wanted to leave people with is how to think about FullCAM. So one of the challenges with FullCAM now is that it's seen as this big monolithic thing, and it's not being broken into the components that separate it, which then makes it very difficult to determine where do you think the problems are with the system, if you've got issues with the system. So I like to break it into 4 pieces. The first piece is the integration framework. So how do all the models and data get pulled together and run? That largely hasn't changed since 2000. It's actually been picked up by multiple other countries. So things like the Full Lands Integration Tool, the Generic Carbon Budget Model from Canada, even the CBM CFS4 these new model frameworks that are coming out actually come back to the core concepts that sit in the FullCAM integration framework. So that's still very robust as a concept. Models and submodels. So there's lots and lots of models in it, as we said right at the start. So you can think about those individual models that attach to the framework. How could they be run in a different configuration? Typically, there's pretty infrequent changes in those. There have been some changes over the last 10 to 15 years that Geoff again will talk about. But these changes to models often create big changes in the results, and they need to be very carefully managed. The last two are the most important in my mind, and these are the things where most of the challenges pop up, and that is calibrations and variables. So what data are the models being fed, and what models are we turning on and off in that process? And so, yeah, are we stuck to the trivial formula, or are we making decisions to run the yield tables, for example? And then if you're doing that, how do you feed those data? And then finally, the interfaces and the usability. So how do you interact with the system? Obviously, there's only been smallish changes to that overall feel of the system with tabs and how everything fits together. Obviously, huge credit to David Evans, who designed all of that at the time, that it's still so relevant. There's obviously a big step forward with the API and the ability to access that. But also remembering that what we're working with externally here is a point model with some estate. It's not the spatial framework. And I think that's a really important point as we move forward, is to think that the spatial framework does actually exist, and it's there and it runs. And there's actually replicates of that running externally in various frameworks as well. At the time I finished working on this, I think I'll just sort of put down these top points, because these were things I was trying to think through, going, I wonder what was, actually what was kind of missing, and what was we trying to do at the time? And it's an interesting question, because we were so caught up in the CPRS that a lot of these things were sliding off, to be honest, in my opinion. But these were the challenges that we saw. So I'm trying to put these down to say, look, it's a continuously evolving framework. We definitely needed to keep going. You've got to keep improving it through time in a sensible way. So this is just a really quick list. We needed to try to get to a fully spatial NCAT. We're looking at how do you revise the M layer, which has been done. Biomass-based age adjustments, new time series allocations and basic density for other species, really getting the spatial and sparse forest work, getting the crop pasture growth models working actually inside the systems. That came up as a question before, looking at how the FPI worked, looking at the national wood product model and how to implement that into FullCAM. And that's a really interesting finding that you'll learn more about soon. How to really think about bringing volume yield table data in as plantations companies came into the system. How do you manage that as a process inside the framework? Looking at remote sensing of canopy closure and new plantation arrange. There's a whole lot of other really interesting ones that I thought there were definitely open questions that we were dealing with back then that I'd argue are still kind of there, which is, do you open source this or not? What global application is there, if any? Although obviously the next generation, Flint and GCBM, have largely done that. What do you do with the nitrogen cycle? What do you do with new remote sensing products coming online? How do you bring those in? And what sort of research programs do you set up in the future? That's the end of me. And after a short break and answer, I'll ask during some questions and a short break, you'll get to hear from Geoff, which is the really interesting stuff.
Yeah, so we've got a couple of questions. If you have some questions on what Rob just covered, Ben, please pop it into the Q&A section. But Rob, do you want to probably touch on the first one? So a lot of the time we talk about running FullCAM, we're used to setting up a plot file.
Yep.
What we don't normally use is the yield table. Yep. And you touched on that. Do you want to elaborate a bit more about what is this yield table and what makes this table?
Well, if you go to the tree species, you can pick how you decide to grow the trees. So under the tree species, and it's under tree species and growth from memory, that gives a series of options, and you can say, I don't want to use the tree yield formula. I actually want to use yield tables. What you put into that then is, for example, a volume. You put that into the system. The main thing to remember with the yield tables is it's coming backwards up to biomass. So it basically just turns it around. So if you were doing stem volume out of FullCAM, for example, from above ground biomass, the tree yield formula, it'll use the allocations to get you the stem biomass. It'll then multiply that by basic density to give you stem volume and back. It does it the other way. So you've got your stem volume, it multiplies it by the basic density for that point. It then includes an expansion factor effectively to lift that up to the other components, from the stem mass up to the other components. And so it builds you an above ground biomass curve. You do your root shoot ratios and other things like that. So it turns off any of the climate impacts on the growth, obviously, because that's just in a yield curve function. Unless, of course, your yield curve is driven from a model that has climate impact in it, in which case it will reflect it. So it's really just inputting an annual table. It can put in monthly if you want as well. You can do it with above ground biomass numbers as well, which I think is a really interesting point going forward around what do you do with things like LiDAR. If you're taking measurements across large areas of sites or at plots, and you know the biomass at a point, above ground biomass at a point, do you start thinking about using this as a calculation frameworks or applying the defaults to your proxies?
One of the other questions we've got here is about how FullCAM accounts for multiple species in a native forest. So where you've got multi-species native forest. Do you want to touch on that?
Yeah. It's a really interesting question about how and with you want to include cohorts or not. We were actually working a bit on this back in the day with Chris McElhenney from ANU. The model itself is really assuming that it doesn't care about species so much. It's saying, look, here's a site. Here's the climate, soil, other conditions. If the native species are there, it should roughly get to this number. Now, it's a bit different when you come to environmental plantings and things, obviously, where you get really different species mixes and you need to make decisions around what's a long-lived tree potentially versus a lot of short-lived stuff. But the core concept is that after hundreds of years, you should roughly end up there. And that's really the piece. Now, if you want it, it does do age cohorts in inverted commas. If you do things like biomass-based age adjustment, it will give you the age of the forest. It'll give you the effective age of the forest. You can calculate the age of youngest trees. So you can do those sorts of things inside it if you want. But yeah, never really focused on that. You could still do it yourself manually by just building separate plots for each one of those things and summing them up. And that's roughly where we looked at doing it. If you get down to a fine enough spatial scale, you can effectively run lots of different pieces. And there's a difference between running a point model versus a spatial model. The spatial model offers up a lot of ability to add effectively cohorts by spatial resolution.
Before I ask the next question, probably also good just to clarify again. So Rob and I work for FinPro. Rob worked for the department for a number of years, ran the inventory, did a lot of the building of FullCAM originally, which is the context which you've just been presented on. We are not part of the department, do not represent the department in any way, shape, and or form. So some of these policy questions about whether or not FullCAM 2024 is going to be allowed under the methods and things like that, we won't be able to answer any of those policy-related questions. But if you want to ask us about, I suppose, nitty-gritty of the FullCAM 2024 or some of the questions of how it works or why it not why it works, but how it works, happy to answer those. So the question here is about when you have a forest that gets cleared and it comes back as not as a forest, but comes back as a shrubby thing.
Yeah.
What does that look like to the inventory?
Well, that's an extraordinarily good question. And it's not necessarily perfectly clear. Part of it depends on whether it comes up as detected as a forest or a sparse area inside the remote sensing products. So the remote sensing has a component that sort of says it's sparse, which is 5 to 20-ish% canopy cover, and then forest is above that. The system isn't looking at sparse, it's looking at coming back to forest. So if it only sees it as sparse, then it's not seeing it at all, basically, as it spins, is my understanding still in the framework. If it comes back as forest, it is actually just going to assume that it comes back as a forest that can still reach that maximum biomass. Now, of course, if you've got field data or you're trying to compare things, you can modify that very easily for your own circumstances using those functions that we talked about before. That's exactly why we put them in at the time. But yeah, if it's just looking straight down from the satellite and it goes on a forest again, then it's going to grow to a forest.
We've got two questions that are slightly different flavors of the same one, asking about, I suppose, thoughts around taking, the calibration approach proposed under the Integrated Farmlands Management method, the IFLM method, and similarly about how plantation growers to be able to modify FullCAM parameters in particular.
Yeah, for sure. Look, obviously, I can't touch on the policy stuff, as Geoff said. We'll just keep saying that as much as we can. around the plantation growers, there's a couple of options there. I mean, the question is, are you trying to calibrate FullCAM to hit the plantation growth? That's obviously one option. If you think you could do that, you could change the effective age, the R through the various parameters, the M through various parameters, and the G values, and you can make that curve fit. That's not overly complicated. At scale, it can potentially start to get complicated. So I guess the question there is, well, of course you can do that. I think it's a very, very good idea, especially for large plantation growers who've got really good data on their systems. But maybe a better idea would be to say, why don't you just use the yield curve function and switch the true yield formula off? The question then is, are you, the emphasis, the responsibility then sits back on the plantation company to produce yield curve and your yield curve. But many of them have that. Sometimes not before age 10, but many of them have that obviously for their wood flow modeling. So one advantage of using your yield tables is that your wood flow modeling and your carbon modeling match on the core data sets. So, but again, how that gets included or how you would do that, that's certainly not a comment about the current policy on the emissions. On the ACCU scheme, that is very clear, that is using FullCAM. But if you were looking for broader reporting for your other purposes, then that's a completely sensible way of moving forward.
The only probably thing I'd touch on there is probably worth considering some of the allocation.
Yes, you must make sure you use the correct time series allocations and basic densities. You will, especially basic density, you'll overestimate carbon very quickly if you just use a yield curve and a 440 for pine, for example.
When I was starting to pull this together, I was really thinking about two groups in mind. So one is the carbon markets. The obvious reason is that FullCAM is used heavily by a lot of the projects under the ACCUs scheme. So it's been used for environmental and mallee plantings. It's got all the regeneration projects, plantation forestry, and just recently the Savannah fire management methods, all underpinned by FullCAM in one shape or another. And one of those versions from 2016 through to 2024. But equally important, I think, especially given the last 10 years of work that I've been doing, is being around corporate greenhouse gas reporting. So looking at scope 1, scope 3 emissions. A lot of organisations, and certainly the work we did, was relying on FullCAM to do the emissions reporting. And that means that the changes that we're seeing that are impacting carbon projects are also going to come through and impact our scope 1 and scope 3 emissions. So I thought it'd be important to touch on some of those as well. So the question I was trying to answer, or will be answering over the next half hour or so, is why results are changing between FullCAM versions. I'm really only going to talk about 4 main drivers. So climate data, the biomass recovery, plant allocations, and harvested wood products. The main drivers of the tree yield formula being the M layer, the G parameter. So you hear everyone talk about G and M, and Rob just explained what R is. I'm not really going to touch on those components, as I feel they're sort of the big behemoths in the room. As to if you change the maximum biomass potential on a site, obviously that will change the biomass accumulation rates on that site. Or if you change G, you're going to make something speed up or slow down. So rather than talk about those parameters, I'm going to try and get into a bit more nitty-gritty around climate data, biomass recovery, plant allocations, and then the harvested wood products. So I pulled out a quote at the top here that comes out of the FullCAM Help Guide, which basically says that in FullCAM, the interannual variation climate conditions, for example, intermittent droughts, are accounted for by annually adjusting the tree yield formula. If you cast your mind back a couple of slides, and sorry I didn't put this in, you'll see that it'll have FPI for a particular year over FPI average in the tree yield formula. So that is, how does the forest productivity index for this year compared to the long-term average forest productivity index for that location? The FPI, in response to one of the questions that did come up, is developed on the basis of climate data, soils data, and I think it's 20-something parameters. I don't think it takes into account CO2 fertilization. Maybe one day it will, but I don't think it does at the moment. So what it does essentially is where the FPI, so when it's a good conditions or above average conditions, the growth will speed up. When it's below average conditions, the growth will slow down. The other thing that climate's going to do is it's going to change the decomposition rates of your debris pools. So when it's a wetter period, you're going to have faster decomposition of the dead organic matter. When it's drier, you're going to have slower decomposition of the dead organic matter. The decomposition side, we saw that swinging a lot in the native forest estate when we're looking through the accounts. So if you are interested in the native forest accounts in particular, and some of the variation, you might want to look at the debris pools and the decomposition rates of those pools. Obviously, the decomposition rate will then influence the soil carbon numbers. As Rob said, everything's interlinked. On the left-hand side, if you want to find out what your FPI is for your location, you can see a little screenshot of the online FullCAM. So if you go to site, there's productivity and there is a forest productivity index, and you'll see a graph through time for that. The FPI, while we talk about the FPI being annually changing FullCAM, the FPI isn't updated annually. So under the 2020 version of FullCAM, we've got climate data through to 2018. And for 2024, we've got climate data through to 2022. There's a bit of a, I suppose, a mix match there. And it's important to be aware of when we're looking at the versions, if you go from 2020 to 2024, the change in FPI means you've added 4 more years of FPI onto your time series. And that's going to impact the growth that you may have already reported or accumulated on that site for those years. So if you already have a forest growing between 2018 and 2022, the growth is going to be impacted. On the left-hand side, you've got the long-term average FPI. The long-term average FPI, which is the yellow line, it's calculated as the average of all FPI data up until 2017. This also kind of gives us a bit of a question is if, as we move forward, it's not clear to me whether or not the long-term average FPI is going to keep extending. Is it going to bring in the data from 2018 through to 2022 as a part of that long-term average FPI? Or is the FPI currently locked to 2017 as it is in the code, which means that you might end up with drift? So one of the questions around climate, future climate, if we go to if the FPI, long-term average FPI remains stable or static, and you consistently get lower, you'll drift away from that long-term FPI. Whereas if the FPI is averaged consistently through time, you won't drift away from the long-term average. You may not drift from that long-term FPI. Hope that makes sense. But FPI is really important in interannual variation. So you can see on the graph below, when we translate the annual FPI into the impacts on growth, it is either increasing or decreasing the growth by, some of these are up to 80% increases in growth rates, or a decrease by up to 60% in growth rates. So this is going to be changing. This will obviously change your growth for that particular year. So when you do a forward projection at the moment, if I run from 2024 onwards, the default is to use the average data. So we'll just take that yellow line at the top and it's going to run the average FPI, which means you won't have any climate signal through your forward projections. But you can change that through the interface to nearest year. You can cycle through the years if you want to. We even use average year of data, or if you really want to, you can manually get in and tinker around with things. The FPI will change the growth rates in a particular year. And when there's an update, that's going to change the results that you've previously reported on for those years, but it may not necessarily change your current year, which I'll show you in the next graph. So this sequence of graph, these sequences are for a same location, but I've offset the years by 2 years at a time. So the first one where it says no FPI, that's where I've done a pure forward projection and it's running the average FPI, which means I'm not getting any climate signal coming through from the FPI. It's just saying, here is my generic forest growth curve, and this is looking at the annual change. So if anyone involved in environmental plantings, you know that the peak growth is around year 6, and you can see that my peak growth is in year 6, then my growth will decline. On the graph to the right of that, I put my plant date earlier, so I'm using real FPI data, and this is the real FPI data for this location. And you can see that the year 6 peak has disappeared because it was a bad FPI year. It was a dry year, whatever it happened to be, which means I had a low FPI value, which means my growth for year 6, or 7 or other in this case, went from 2.5 tonnes down to 1 tonne per hectare for that year of change. So this is going to start materially impacting your previously reported numbers. Whether or not it changes your current carbon stock depends on the sequence of FPI values. So it can change the abatement outcome because the FPI is never going to be up to date, I don't expect. So we're always going to be a couple of years behind. One thing that we've noticed is that there is a step in the forest productivity data when the time series moves from being real data to being projected. So in 2020, the 2020 release, you'll see that there is the data comes to 2018, which means that 2019 might look really weird. In the 2024 release, the data goes through to 2022, which means that 2023 FPI data might look really weird. And what FullCAM's doing is it seems to be averaging, like countering whatever the last year's FPI was. So if the FPI was quite high, the first year in the new time series, the projection will be equally low. So if it was up 40%, the next year will be down 40%. If it was down 40%, the next year will be up 40%. So what we're finding is that when you have that transition year from real data to the projection, you have this really noisy year in the middle, in that transition year, and it can change dramatically when there's an update in the data. So when there's that update, that means that it will be replaced. One of the other things that climate is doing is it is impacting the debris pools. So as I said, the wetter periods, it speeds up the decomposition rates, and in dry periods, it slows down. There's two functions that do that, or the two main ways that FullCAM will account for, I suppose, climate in the decomposition rates. And that's through mulch style sensitivity and also through soil style sensitivity. In simple terms, mulch style is a simple calculator using the available moisture and temperature, whereas the soil sensitivity is more complex. It's linked to ROC, the soil carbon model, but it'll change the rate of decomposition of your debris pools. So FullCAM 2020, you've been running that, and you start to look at 2024, there was a shift from using mulch style sensitivity to soil style sensitivity, and that has impacted the growth that you'll get, so the carbon accumulation of your debris pools. So I'm just going to take a step back from the debris pool data and just show this slide, which kind of goes onto that FPI data that I was trying to explain a lot easier with a graph. So this is, you can see the yellow and is the where FPI data goes through to 2022. The green on the bottom graph goes through to 2018. So if you look at 2019 in particular, you can see that the reported FPI for 2019 under FullCAM 2020, which is going to FPI to 2018, has a value of a bit over 4. Whereas the actual data, when it comes back to 2022, it dropped back down to about 2.75. So this year, if I was reporting this year, I would have a material change in the carbon accumulation for that year between FullCAM 2020 and FullCAM 2024, purely because of this correction in the FPI for that year. Likewise, you can see in 2023, where the preceding year in 22 was a good year. We had a high FPI value, wet year in 22, so it's almost back at 4. That averaging that I was talking about means that in 2023, my FPI drops all the way down to 0.5. So the growth in that year is projected to be tiny relative to the preceding years. So when that data falls in your peak growth period for your project or for your past reports, then it's going to start doing some pretty funky things with your numbers. Whether or not it will have a material impact on the long term, it depends on basically the time series of your FPI. So as I said, from 2020 to 2024, there was an update to not use the mulch style sensitivity, but to use the soil style sensitivity. And you can see basically that you have in this particular example, a much greater increase in the debris pool over previous reporting. And this is really the above ground biomass will change a little bit from the updates in version, but from 2020 to 2024 versions of FullCAM, the main change I was finding was in the debris pool. In this case, I had a 70% increase in the debris pool, which made it which ended up with a 12% increase in total forest biomass for that site. It increased the debris from being about 22% of the tree biomass, as in terms of relative terms, to 38% of the tree biomass. So a really big change for this location. As a project proponent or as someone looking at my Scope 1, Scope 3 emissions, my main take home is that your debris may go up. It may also go down. Western Australia in particular seem to be very sensitive to the soil types. And it's a lot more sensitive to annual variation. There's a lot more annual variation driven by the climate than what we could see with the soil style sensitivity. And you can see that in the graph above, where we've got dips, and a little bit more chunkiness coming through with the actual variable. So you can see the red line, that's where I've got climate accounted for. So you can see in some of the years I have a drop in my debris pool because of fast decomposition, or I might have an increase because of slow decomposition, whereas the soil mulch style variation is really minimal for those same periods. Next thing I wanted to talk about was the biomass recovery type. So this is a pretty fundamental change to between the versions. So within FullCAM, there are two types versions of FullCAM that people are using for projects. There's two types of biomass recovery. What I'm talking about here is when there is a disturbance event, that's either a thinning event or a fire event. It's how does the model respond? How does it reaccumulate that biomass? There's the age-based adjustment and there's a biomass recovery function. So the age-based adjustment is where the effective age of the forest is recalculated based on the remaining amount of biomass. So you can see here, if you follow the light grey line, hopefully you can see that on the screen, that's the tree age used in the tree yield formula. And then the red line is the age of the oldest trees in the forest. So you can see in this example, they're tracking along and they're saying that means basically it's an even age cohort in the model. But then I have a disturbance event. I have a thin event in this situation. And it means that the effective age changes and it's now following the grey line. So to put that as a little animation, at the end of my thin event, it looks at how much biomass have I got here. It goes back and says, well, for that amount of biomass, I should be growing like a younger forest. And essentially, it projects forward the growth rate of that younger forest. In the FullCAM 2020 version, this was for thin events, you had the biomass age adjustment, and under 2024, you have the biomass recovery function. The biomass recovery function is where, I'll try and work out the best way to explain it, but basically you end up with two growth curves and they get added together to get a recovery. So the forest itself actually continues growing at the same age consistently through time. So if you follow that terrible colors, but that light green line, that's the age of the forest. If it kept growing, it'll follow that same rate of change through time. And then when there's a disturbance event, there is a secondary function, which is a biomass recovery function, which will then get added to the previous growth. What it does mean, or the take home really, is that the recovery function means, biomass recovery function means that the forest will always return back to the standard line. So you can see in this situation, the dark green line, there's a disturbance event, and then it grows back. Within 20 years is the default for plantation, 60 years for native forests. Within that 20 or 60 years, the forest will always get back to the same curve. So the only way it won't stay on that curve if I have another disturbance event. In contrast, the biomass age adjustment for a point in time, it won't actually get to the same, it won't catch up. The forest will always be held back. So it'll be recovering. And eventually, if there's no disturbance to 1,000 years, it'll get to the same point. But it ends up meaning these two forests are behaving differently. This does start to change the biomass accumulation rates across your projects. So 2016, you have age-based adjustments following thins, not really applied for plantations, but it will be impacting any of the native forests if you're running those. But it will have a biomass age adjustment for fire events. 2020, as said, it's only age-based adjustment for thin events, and then it's got a simplified biomass recovery function for fire events. And then 2024 is where the thin events and the fire events are now both using a biomass recovery function. So this does two things. One is it will generally speeds up the recovery rate over the biomass age adjustment, but it also means that you need to have synergies now between fire and thin recovery functions, which is a bit more unique, I suppose. So we can't have a fire event and a thin event recovering at different rates. Otherwise, it doesn't seem to work. Overall, projects that are using the biomass age adjustment, biomass recovery function are probably going to benefit from using that. The BRF underpins all of the FullCAM modelling. So all of the recovery rates that you're seeing under there is being driven by that biomass recovery function. So any changes to that function would therefore impact any savanna projects that are out there, or plantation forestry if it ever moves over to the updated FullCAM version. So a good one to keep an eye on for updates. Allocations. So as Rob was saying, essentially that from the M layer, all we're developing for the tree yield formula is the above ground biomass component as a whole. It just says, here's my big lump of biomass that belongs to the above ground biomass, and that's what's derived from the tree yield formula. The next step in the model is to partition it into the individual components, so leaves, branch, bark, stems. The low ground biomass is calculated as a fraction of or a function of the above ground biomass component. So even though it doesn't necessarily present it that way, the way that these fractions get applied is slightly different. The leaves, branch, bark, and stem get kind of lumped together and they get partitioned across those values, whereas the roots are a function of the total above ground biomass functions. If you want to look at your biomass, it's under the trees tab. You can go under growth, and then you can look at the allocations underneath of those. The species that we've got in here, the species list kind of masks the depth of the calibrations that are in the current versions of FullCAM, or the main used one, the 2020 and 2024. So while there's 22 native forest species across these two, there's actually only 2 calibrations for the allocations. There's basically a high rainfall and a low rainfall zone, which have different root to shoot ratios and branch ratios and all of those things. So I think there used to be quite a lot more. Then it got simplified. And in that simplification, it also went from a time series allocation that Rob presented, where the proportion for stem, branches, and bark used to change through time, to now having a single value for all time. So it's moved, they're kind of like a simplification of the calibrations that's happened in the last few years. What does that mean? It means that numbers are going to change because your allocations have changed. So apologies, is a bit messy, but we'll step through it quickly. From 2016 through to 2024, I might talk about 2 pools in particular. If we look at the root mass in here, the fine fraction, 2016, it used to be 0.0031, as a number, and it went from 0.0031 to 0.032, which is a very small number, but it is a tenfold change in the absolutes. So these little numbers, they look like subtle numbers or small numbers, but they can actually have a really big impact, which I'll show you on the next slide. The stem allocations for radiata, I've converted the top tab. The top numbers here are what's in FullCAM. These are the numbers you'll see. And what I've done below is try to put them in a more friendly version. So what we've got is the percentage of the stem relative to the above ground biomass and branch, bark, and leaf. So you can see here for Pinus radiata at age 30, for example, it went from a 78% of the biomass was in the stem at age 30 to saying 62%. Again, that means that there's a 20% decrease in that allocated stem volume. So a 20% decrease in stem volume will translate to a 20% decrease in your harvested wood products that are coming from that component as well, because of all of these flow-on effects. The increase in roots from 20% to 32% of the total biomass, or relative biomass to the above ground biomass, also means that there was higher turnover through the fine roots. So more carbon was going into the roots than it was previously. That's increasing the carbon on site because of the root calculation. So there's increase here in the biomass from roots. There's a decrease in stems, which means a decrease in harvested wood volume. One of the little things that we also found from 2020 to 2024 is in particular for environmental plantings. There was a change from 2 decimal places to 3 decimal places. So it was relatively the same number, or very close to it, for environmental plantings. But essentially 2020 was a rounded up version to 2 decimal places. That change from 2 to 3 decimal places was resulting in a 1% change in carbon stock for our locations. Doesn't seem like much, or it may not seem like much, but it can start to have quite big implication. The other point that I was going to make was that moving from a time series allocations to a single allocation really shows the importance of considering what question we need to, what we're trying to answer. So when are we trying to say what is the average allocation across time? So if we look at a young tree and an old tree, what's the average allocation of stem mass? Is that what's important to us? Or if we're looking at, well, actually, I care about harvested wood volumes. I don't care if I'm wrong in the younger years. I want to be right at the time of harvest, which means that I might want to bias my results and say, I want to look at the stem volume at age 30 if I'm going to use one number, because that's the most important time form. The other point I'll probably just make here about big variations, the leaf mass obviously was another one there that changed quite dramatically from being 1% of the total carbon stock of the radiata to 11%. That's going to impact your debris pools, your turnover, which is going to impact your soil carbon, all of these linked models that flow through. So on that, this is looking at FullCAM 2020. So this is looking at Pinus radiata, and just so some of the challenges that you can have if one thing changes but the other one doesn't. So in this case, the fine root proportion increased, but the turnover rate wasn't modified from memory. And it meant that if we had you saw in the slide, a 10 times increase in the fine root matter turning over, and it became a little basically carbon pump into the soil. So the top graph is the production rate of fine roots onto the radiata, and you can see the fine roots is vastly exceeding the production rate of the stem. So more carbon's moving through the fine roots than was going through the stem mass. And that resulted in an increase in soil carbon under this example, where the soil carbon was increasing more than the tree biomass was increasing. We found this in particular when we were doing the work for the NRC. And for that reason, we opted not to include soil carbon from FullCAM-based results for our reporting purposes, because it would have vastly exaggerated it. This is a modern issue that has been corrected with 2024 update. But if you're using 2020, it's to keep an eye out for that. Harvested wood products, I just wanted really to touch on the harvested wood products because it's something that is always there and we don't really pay too much attention to it normally, but it can be quite important for both plantation forestry method. There's the proposed native forest method, which this will impact. And there's also obviously your scope 1 and 3 emissions reporting, which this will impact. What we're saying is I have carbon, it leaves the forest, it goes into wood, then what happens to it? Under the documentation of FullCAM, it suggests that there is a simple decay curve. So that top screenshot is the FullCAM interface where you've got a decay curve for a particular pool and it's losing a set % per year until it all disappears, and that rate will vary based on product type. So it's going to vary based on construction wood, and it'll vary on pulp and paper, and all these things are going to have a different rate. This is where we kind of actually got a little bit confused, and there still are. So I suppose if the department's on here, they might be able to shed some light onto it. FullCAM doesn't match the documentation for the harvested wood products component, in that when we break down the components and model them individually, so you can see this bottom graph down here, we're seeing a bit of an odd pattern where it looks more like there is a protected pool that's losing a little bit and then it speeds up. This may or may not be consistent with the national inventory. We're not quite sure. But what we can say with certainty is it doesn't match the documentation and it doesn't match the decay curve. The interface doesn't actually impact any of these rates. So our main conclusion here was if you're doing anything with harvested wood products or looking to change the harvested wood products, probably proceed with a bit of caution. I don't think the interface actually does anything to the modelling of those harvested wood products. And we're not sure entirely what FullCAM is doing with those products. Another thing we've found in here is that some carbon fractions are being applied multiple times to some of the pools. So the reported pool is half of what it should be. So 1 tonne moves out of the forest into harvested wood products, but only half a tonne turns up in the wood products. So there's some funky stuff happening with the harvested wood products. And while it's important, I think just a degree of caution on how that, if you're looking at those products. And I suggest would be a good thing for maybe for AFWI and others to look at. So what were my final thoughts about all of this? And so hopefully folks were following along as I'm rambling through some of the things that I've found over the years, really. But FullCAM is a powerful but sensitive modeling system. So its flexibility is a really asset to it. You can change any parameters. There's like 450 parameters inside FullCAM, and you can change them all. And with the exception of harvestable products, it will do something. But you do need to be careful when you're tinkering around and changing parameters. So a small change, like that rounding issue, can have a big implication. 1%, yeah, what's 1%? And said, well, 1% might be 0.3% or 0.4% of your IRR for a carbon project. Suddenly 1% becomes a problem. These updates, like the FBI updates and other things, does mean that everybody needs to be comfortable with change and be willing to have some of these more difficult conversations, that our numbers may not be set in stone. So if you put out a report for 2022 or 2023 and say this was our emissions profile for 2023, if you rerun it in 2024, next year, and update it, that data might have changed but underpin your previous reporting year. So it's never actually locked. And I think that soil example is a good one to highlight that if you change one thing, it might change other things in an unexpected way. So as Rob was saying with, let's just spend our numbers and throw it into the tree yield, the yield tables. Well, if M's not the problem, that's why you're underestimating it, it's the allocations, then you might not be fixing the thing that's broken. And that might then break your soil, your debris pools, or it may break other things. So it's not always plug and play with individual parameters that are in there.
This was a never-ending issue back in the 2000s as well, to be honest, because we always got claimed that, the claim was always that FullCAM wasn't transparent, despite the fact that we made the system completely available, open, all the input data was there. The only thing we didn't do was open source it. And we provided, literally meters of reams of paper documents in the tech report series that showed all the data and how and why we did things, and, full inventory reports of hundreds of pages. So it's the transparency of FullCAM, compared, to be blunt, against most other systems around the world, is actually extraordinarily high if you don't count the ability to look into the code. I would say that the issue is that even if you release the code, as showed before, it's extraordinarily large, and you end up it's no longer a black box. It becomes, in that lingo, a white box, which is great. All the code's there, but who can actually read through it and understand how it all works? So transparency is a never-ending issue when you get to these large systems. The most you can do is continuously, at every single update, provide really, really strong documentation, really good processes around those updates, so that every time there is an update, it's documented extremely well. You say, here's what changed, here's why we changed it, here's the science we changed it on, and here's the impact of that change on these results. And that's a significant issue at the moment, I would argue, because you only have to look at the wood products thing to realize that there's been a very major update somewhere in FullCAM, but it's not documented. And it's certainly not able to be changed or tested in the system because the parameters don't do anything anymore. So it's a really big issue. It's one I'd recommend. It could be a really long conversation. We dealt with the same thing when we built the second generation tool, the full lands integration tool, when we decided to open source that. That was fantastic that it was all open source, but then people started saying it's not transparent because it's too big. So with that, more philosophical in many ways than anything else.
So the issues with the harvestable products, it will have possibly some implications. At least it's consistent in the bias. So that pool would mainly seem to affect the pulp and paper pool. So I suspect any impact may be very minor. It's more, I suppose, it's just not doing what you'd expect it to do. But whether the impact is there, I'm not sure what the actual quantification impact will be. It is in 2016 as well as in 2020, so it's been in there for a long time. That step change model of the straight decay curve. So all plantation forests at the moment will have that, and presumably when it gets corrected for, that'll flow through. The main thing is we're just not sure what the parameters are that sit behind it, and then how closely that does or doesn't align with the inventory. So looking for that, if we're looking for consistency with inventory, then the improvements that are there, or the start of doing it to reflect what's in the inventory is a great progress rather than a simple decay curve. But yeah, it's a bit unclear at this stage, and maybe this is something the good folks at AFWI might think about.
That's a really important one, and I wouldn't say the original decay curve in FullCAM was never used for the national accounts for a very good reason, multiple good reasons, primarily dealing with import, export, and different accounting rules. But also the straight decay curve was not something that we thought was particularly useful. So the move to a step change approach as the same as basically based off all the work that Gary Richards and Fabiano and myself and others did over the years, but Fabiano and Gary in particular put that into the national accounts, is a far more consistent and a far better structure than what we had in there originally.
Yeah.
Chris Brack's comment on the rest of the world didn't trust claims of Kyoto. I can personally attest to that. That period, it's almost with a book in itself. It was extraordinarily difficult just to demonstrate that our emissions estimates for the sake of Kyoto reporting were actually sensible and could be accepted. There was a huge degree of animosity against Australia at the time, especially around Article 3.7 deforestation, and that flowed through to this. So, if you're looking for sort of how would FullCAM work, it got run through the ringer for years on the back of those analyses, and generally came out pretty well, I would argue. So
I've got to say, like, FullCAM as a modelling is a fantastic modelling system, and the decades, it's been 2 decades of work to get to this location, and it's underpinning an awful lot of great work out around Australia in addition to the national accounts. So I just wanted to reiterate that there will be a continually evolving, presumably, and that's what AFWI's work is going to be looking at here. So the questions are now sort of like where best can you spend time and effort to do it, because no model is ever going to be perfect. There's about, well, where do you need to focus effort, hopefully, and that's where we'll also be interested in.
Conscious decision on modelling emissions from forest operations. I take it you mean fossil fuels. It wasn't a conscious decision at all. It was actually a decision of, we do really want to do that. We actually wrote a full design for a system called FullCAM, just to add to that enormous list of models that were stuck in FullCAM. The idea would be that you would simply attach litres used per harvest and have some other functions in there at the time, which would then allow you to track that into, it was very important at the time in terms of trying to track into the bioenergy and the displacement models. To be absolutely honest, we just never had time. It was always number 2 on the priority list, given everything else that was going on. And at the time, of course, we didn't have an emissions trading system. It wasn't part of an ACCU method. So we went, yes, we need that. We just never did it. So a bit similar to what Geoff just said, that is another thing that could be extraordinarily useful to consider around building that. And I would argue that probably that design remains pretty similar. And FullCAM, yeah, it's a terrible name actually, Darren. Thanks, though. Ooh. Oh, the ISO standards. Yeah, good question. Theoretically, the system is able to cope with most standards in terms of reporting, because you're doing time series, it's complete, it's consistent, it's got all of your core piece. A lot of the accounting rules and everything really come back to the stuff that was written in the IPCC back in the late 90s and early 2000s. The core principles haven't changed. Well, I haven't read the new ISO document in detail. I've only tracked it a little bit. But it's not dissimilar to thinking about what may have happened under the greenhouse gas protocol had it not failed in its ability to cover forests. Is that it's the piece of what you do to feed that model. So there may be cases, and Jeff's worked a lot on this on scope 1 and scope 3 emissions, where methods do not allow model-based approaches. You must use measurements at every 5 years, in which case you would need to start thinking about either adjusting the model or using yield tables or doing something different. So yeah, it's again that piece. One of the core philosophies of FullCAM and the NCAS development was to try to make the outputs as far as possible and practicable policy independent, so that you could then slice it up into different buckets. So we would try to estimate the emissions and removals all over the place. And then we would, for every piece of land, we'd say, oh, that piece of land at the moment belongs in this reporting bucket or this reporting bucket. At the end, all the numbers added up, but they might have been in all different buckets. And it's exactly the same with the ACCU scheme around at the moment. For example, definitions of forest and how that gets used in methods and what buckets that get listed into. So it's a live question across all policy.
Yeah. And I mean, we use, we rebuilt FullCAM and it's a different version. So we could run it for our needs, a spatial version under Full Pro for doing general reporting purposes. Although I haven't kept up with the latest update on the sheet protocol about where that landed. Nowhere. But yeah, but by and large, it was useful because it's got the completeness and the capacity to look backwards and forwards, exceedingly useful for doing those scope 3 emissions, in particular land use change emissions for reporting purposes.
I should note that framework that Geoff's just talking about, then Geoff applied globally, basically. So it was the same spatial type of framework running across, but just picking up different input data effectively. So yes, we had a full replicate of FullCAM running spatially, pretty much exactly the same as what runs in the department for the national accounts, give and take a few things. But that system was actually the core framework, again, with being run all over the place.
We seem to be out of questions. So if there are any burning questions, now's a good time to answer them. Otherwise, we can throw to
Patrick there's one more anonymous for those who use FullCAM for the ACCU reporting. Yeah, look, the anonymous attendee question. I think this is exactly. I'm sorry, I'll read it out. So for those who need to use FullCAM for their ACCU reporting or just general awareness, where do you think they should start to look to get a bit of understanding of the model? Is there anything that we could be doing better to help support more general users? And I would say very strongly yes. That's this we would hope is the starting point of that process. That's why Geoff and I decided to open this up as a general discussion. And yes, we've probably droned on about the difficulty of policy and things a bit too hard and a bit less on the usability of the system. But if I was to look to a country or a process that's done this really well, it's Canada. So at the same time as Australia was building FullCAM, Canada was building the CBM CFS3, the Canadian system. Remarkably similar concepts, just runs on a slightly different framework. Definitely worth looking at if you love this sort of carbon modelling. I mean, who wouldn't? But they actually had a dedicated training person. They've run upwards of 100 training courses over the last 20 years. They've got full documentation, training guides, user guides, demo systems, everything sitting there in the background. What that's led to is the EU runs CBM CFS3. Lots of countries have picked up and run that modeling framework now for their systems, and they're actually updating, interestingly, to a Flint-based system, a full lands integration to a basically second-generation FullCAM framework process at the same time to meet spatial reporting requirements. So, but even that process, again, the Canadians have thrown so much effort into that training and support piece. So there isn't a lot of places to go. If you want to really learn it, without being too boring about it, I would download Cam4 as a starting point and have a good play with it. Because if you get through that, then you can quite quickly understand what the modeling's dealing with. EUPD data.
If you just want to add on to that, I hope two take homes I'm hoping that comes through is going back to these points about the confusions or misconceptions. FullCAM, and I hope it's clear now, FullCAM is more than the tree yield formula. And what we find at the moment is a lot of discussions around what FullCAM doesn't do is done very generically. And everybody, you might be talking about the FPI data and you don't like that component, and someone else is talking about allocations, they don't like that component, or someone's talking about the M layer, or someone's talking about all these little elements, but it gets lumped as FullCAM. And it's very hard for these discussions to progress if we're not talking about the same things in the same language. So I would echo Rob's point about the need for, I suppose, either more training or more opportunities where the CMI or other groups can do this, or the department. But I think it would be very useful, given the high volume of people, as we've got however many people on this webinar, use FullCAM. There really is its need for better understanding of what it is, so we can have a more nuanced discussion around how to improve things.
Just looking at Dean's question here of Cam4, yes, we can try to get a link off to that. It's somewhere on Trove. Look, honestly, I'm happy to just send it to people. I've got an enhanced version that I modified years ago that people can just have. Applying the plantation forestry method definitely produces very conservative biomass estimates compared to inventory, which I'm fine with from a robust carbon credit approach, but where are the constraints that produce that result in FullCAM itself or in the methodology implementation of FullCAM? It's in the methodology implementation of FullCAM. It's not in the process itself. It's the data you feed the thing. So there's multiple ways of looking at the conservativeness. There's obviously the issues with the allocation that drives down the wood product numbers, especially at final harvest. So there's a huge degree of conservatism. You would probably argue from the lack of time series allocations. In the 2016 version, you'll find a degree of conservativeness because going back to Chris Brack's point, we were really under the pump on Kyoto. And so we lined everything up to the inventory and then we took a little bit off because, that was a core component for us. We'd always assumed that would be slightly updated as we went forward. So that's the first point. I think the second point starts to come, and again, this is an AFWI question, is do you start looking at yield tables instead? There's multiple good reasons for doing that beyond getting a bit more carbon. One of the simplest ones being is that your timber yields and your carbon numbers then match, which makes valuations easier. So there's a whole lot of processes there that can really help, that it needs a broader thought piece.
Well, and your carbon numbers might also go down.
Yes, there are points where it will go down. Yes, exactly. And you only have to look at that region example I gave where there are, in the 2024 version, there are calibrations that are giving MAIs for pine in some regions well in excess of 45 cubic meters a hectare a year over 30 years, which I think most people on this call would suggest is an overestimate of the pine productivity of this Australia. So yeah, Barry, look, same problem. I just go back. I think this is an industry issue. It's very, very difficult to get the training sessions on this. As Geoff showed, the allocations are actually difficult to understand themselves because they apply year by year. They're not actually a allocation at year. Also, the forest yield table is just a dump in of basically a current annual increment number, but you should be able to find that in the FullCAM help. Theoretically, that wouldn't have changed over the last 20 years.
No, it's buried in there somewhere. The G parameter is always under the growth component of the tree. The little trick there is, though, you've got to, when you plant the tree, you've got to plant it to say user defined G parameter or GNR parameter, but user defined, not block, belt, whatever. Then you can modify it. Sorry, the question there is where do we find the GNR parameters and what's being used on a model and how can I modify it? So yeah, just explaining that the GNR parameters are under the growth component of the tree, whereas you need to make sure that when you plant said tree that you use a defined if you're going to be modifying any of those parameter types. But it goes back to that point, as Rob was just saying, that there is a need, I think, for maybe more advanced users about how to run FullCAM, how to modify it, and how to tweak it. Because FullCAM is a lot more powerful than the guidelines allow you to do, and the guidelines deliberately limit what you can do in it.
Yeah, and I'll just add to that on that G thing. This is one of the issues coming through that we're finding in the online version of FullCAM is there's boxes to put parameters. You can change the parameters in those boxes. The wood products is the best example, but G is another good example. You can change a parameter, it doesn't do anything. You just haven't clicked a box in another area. Yeah. And so you get it's a bit like the biomass-based age adjustment. It looks like it doesn't do anything unless you go all the way down into the tree species component and remember to change the age of the trees from the maximum to the average. And if you do that, suddenly the biomass-based age adjustment curve works. If you don't, it does nothing or very little. So there's a whole lot of little tricks there that have slipped in through the interface over time. Of course, one of the issues for the department is that because people also aren't looking deeply into this, they're not finding out about them. So there needs to be a really clear sort of feedback, very positive feedback process into this to say, hey, we're working on this. It would be much better if blah. Because at the moment, the industry is just becoming a taker. It's not driving. And there's no other questions. So hopefully it was all extraordinarily useful. Patrick, did you want to give us a summary and go from there?
Yep, I'm not going to pretend to give a summary. Rob, that's very much. Now, I'd just like to thank both Rob and Jeff for providing a useful overview of the evolution, the use, and some of the issues with FullCAM, as well as a deep dive in particular with Jeff into various aspects of its application that have direct consequences in forest carbon accounting. The focus is mostly on forests, but there's certainly overlap into other land uses here in Australia. I'm sure for those of you in the audience, this has provided you with some useful context, answered some lingering questions, and I hope it has also raised some new questions. I think it was the physicist Enrico Fermi who said that he walked into a lecture confused and he walked out still confused, but at a higher level, and I feel that's appropriate here. So, as Rob mentioned at the beginning, we'll be providing everyone with the slides from today's talk, so I hope you didn't try and scribble it all down. If you have further questions, feel free, please, to reach out to us. Ellie McSheedy, our center manager, will be sending out an email to everybody with the slides and the center contact details. And so again, thanks for joining us, and we look forward to carrying on this and other conversations about forests and carbon in Australia with you over the coming months and years as part of our AFWI Center for Climate Smart Forestry. So thanks again, and enjoy the rest of your day.